Why does a balloon fly away when you let it go? Why does a car slow down when you press the brakes? And why does an apple fall straight to the ground? The answer behind all of them is forces. In this lesson, we'll break down the types of forces you need to know for the exam and how forces affect motion and shape. From friction and gravitational force to Upthrust and Hooke's law, we'll use simple examples and step-by-step explanations to make things crystal clear. Let's begin with the basic question. What is a force? A force is simply a push or pull that one object exerts on another. Forces can do all sorts of things. They can speed things up, slow them down, change their direction, or even change their shape. Sometimes forces cause things to move. Other times, they stop things from moving. Now, how do we measure the size of a force? The unit we use is the Newton, written with a capital N. It's named after Sir Isaac Newton, the scientist who figured out the laws of motion. And just to give you an idea, 1 Newton is the force needed to make a 1 kilogram object accelerate by 1 meter per second squared. But don't worry too much about that right now. Just remember, the stronger the force, the higher the Newton value. Forces come in different forms and act in different ways, and we will explore each type shortly. Sometimes, the effect of a force is easy to see, like a person pushing a shopping trolley, gravity pulling an apple down from a tree, or a powerful machine crushing a car. Other times, forces act in ways that are less obvious, like the tension in a stretch cable. But whether visible or not, forces are always there, influencing how objects move, stop, or even change shape. Let's say you're trying to push a car. The moment you start pushing, you apply a push force on the car. To keep things simple, let's focus only on the forces acting on the car, not on you or the ground. As you push, you'll notice it's hard to get the car moving. That's because there's another force acting against your push. This opposing force is called friction. Generally, friction arises whenever two surfaces slide or move against each other. Each surface pushes back, creating the friction force. In this case, it mostly comes from internal friction inside the car, like between moving parts in the wheels and axles. This friction resists the motion you're trying to create, so it's unhelpful here. But friction isn't always bad. It can be very helpful too. For example, when a car engine drives the wheels, it's the friction between the tires and the road, often called grip, that actually allows the car to move forward. On icy roads, even powerful cars struggle because there's too little friction between tires and ice. The wheels spin, but the car stays still. So friction can prevent motion or enable it, depending on the situation. In machines, we often try to reduce friction so that the parts run smoothly and last longer. But with tires and brakes, we want more friction for better grip and control. Sometimes friction gets in the way, and sometimes it's exactly what we need. It plays both roles in everyday life. Okay, back to the car. So far, we have looked at horizontal forces like push and friction. But what about the vertical forces? The most obvious one is the gravitational force, or weight, which is caused by the Earth pulling the car downward. This force always acts on the car, even when it is just sitting still. Imagine pushing the car off a cliff. Gravity's pull becomes obvious as it accelerates downward. But if gravity is always pulling down, why doesn't the car sink into the road? That's because the road pushes the car upward with a force called the normal reaction force. Normal here means perpendicular to the surface. This upward force balances the car's weight on flat ground. So vertically, two forces act on the car. Weight, pulling down due to the Earth's gravity, and normal reaction force pushing up from the road. Together with the horizontal forces, that makes 4 forces acting on the car, all from other objects around it. You, the road, the Earth, and even the car's parts. Remember, every force is the result of an interaction between objects. Now let's look at a few other important forces: magnetic and electrostatic forces. These forces don't require contact. They act through space. Magnetic force acts between magnets or between magnets and magnetic materials like iron. Opposite poles attract while like poles repel. Similarly, electrostatic force acts between charged objects. Opposite charges attract, like charges repel. Here's a fun example. Rub a balloon on your hair and stick it to a wall. That's electrostatic force at work. The next one is drag force. When an object moves through a fluid, like air or water, the fluid particles push back, resisting the motion. This force is called drag or air resistance. You'll feel it when you cycle fast or stick your hand out of a moving car window. The faster you go, the stronger the drag force becomes. That's why cars, planes, and even sportswear are designed to be aerodynamic, to reduce drag and move more efficiently. Next, we have upthrust or buoyancy force. When you drop something in water and it floats, that's because of upthrust or buoyancy force. Upthrust is the upward force a fluid exerts on an object when it's immersed in it. If upthrust is greater than the object's weight, it floats. If it is less, it sinks. Boats float, balloons rise, and swimmers stay afloat, all thanks to upthrust. Now that we have looked at different types of forces, there is something else we need to understand. Forces don't just have size or magnitude, they also have a direction. That's why we say that the force is a vector quantity. For example, pushing a box with 10 newtons to the right is not the same as 10 newtons to the left. Same strength, different direction, so it's a different force. To show both size and direction, we often use arrows. The length of the arrow shows the force's size. The arrowhead shows the direction it's acting. This becomes really useful when multiple forces act on an object. Remember the car we looked at earlier? It wasn't just experiencing one force. It had a push force, friction, weight, and a normal reaction force, all acting at the same time in different directions. To understand how these forces affect the motion of the car, we need to combine them. And that's where the idea of the resultant force comes in. The resultant force is the overall force acting on an object after you add up all the individual forces, taking both size and direction into account. Okay, let's go back to our car example and see how resultant force works in action. Imagine you're pushing the car with a force of 100 newtons to the right, but there's a friction force acting against the push force, also 100 newtons, but to the left. These two forces are in opposite directions, so we treat one as positive and the other as negative. So what's the overall force? Let's say push is positive and friction is negative. That becomes 100 newtons minus 100 newtons, and this is equal to 0 newton. This means that since they cancel each other out, the resultant force is equal to 0. And what happens to the car? It doesn't move. Now let's look at the vertical direction. The weight of the car pulls it down, and the normal reaction force from the road pushes it up. These two forces are also equal and opposite, so they cancel out as well. This means no vertical movement, the car stays firmly on the road. But now, let's say you bring in a friend to help you push. Now there are two people pushing, 100 newtons each, both to the right. That gives a total push force of 100 newtons plus another 100 newtons equal to 200 newtons to the right. Friction is still pushing back with 100 newtons to the left. So the resultant force is positive 200 newtons of push force, negative 100 newtons of friction force, and this results in an overall resultant force of 100 newtons to the right. This time, the forces don't cancel out. There is a net force of 100 newtons to the right, so the car starts moving in that direction. That's the power of resultant force. It tells you whether something will stay still, keep moving, or change its motion. Forces don't just affect motion, they can also change the shape of objects. Let's take a simple example. If you stretch an elastic band, it gets longer. You're applying a force and the band's shape changes. This kind of force is called tension, a pulling force. On the other hand, if you squash something, you're applying a compression force. Almost all materials change shape a little when you pull or push on them. but how much they change depends on the material. You can stretch a rubber band quite easily, but try doing the same with a steel rod the same size. You'll need a huge force to make even the tiniest change. Some materials like glass don't change shape much at all. Such materials are brittle. That means they'll break before they bend or stretch. Other materials like springs or rubber bands are elastic. They change shape when you apply a force, but once you let go, they return to their original shape. But not all materials do that. Take modeling clay, for example. If you press or stretch it, it stays deformed. It doesn't bounce back. That's because it's plastic, not elastic. Plastic materials don't return to their original shape after a force is applied. The change is permanent. So, to sum up, elastic materials change shape but go back to normal once the force is removed. Plastic materials change shape permanently. Brittle materials break before they bend much at all. Forces don't just move things, they bend, stretch, squash, or even shatter them. Springs are coiled pieces of metal that can be stretched or compressed when a force is applied to them. They are used in all sorts of everyday things. In cars and bikes, as suspension systems to absorb bumps on the road. In beds and chairs to make sitting and sleeping more comfortable. And in many other cases. To choose the right spring for the job, we need to understand how they behave under force. Springs are elastic, which means they stretch when a force acts on them and return to their original length when the force is removed, but only up to a point. If you stretch a spring too much, it goes past something called its elastic limit, and after that, it won't bounce back to its original shape. A scientist named Robert Hooke discovered an important rule about how springs behave. He measured how much a spring extended when different weights were added and found something interesting. The extension of the spring was directly proportional to the force applied. In other words, double the force, double the stretch, or F proportional to delta X. This relationship is called Hooke's law. And when you plot it on a graph, force versus extension, you get a straight line through the origin. But Hooke's law only works up to a certain limit. If you keep increasing the force, eventually the graph starts to curve. That point is called the limit of proportionality. Beyond this point, the spring stretches more than expected for each extra bit of force. And if you keep going, you'll reach the elastic limit. After that, the spring is permanently deformed. It won't go back to its original shape even if the force is removed. This same principle applies to metal wires too. They also follow Hooke's law up to their limit of proportionality. But not all elastic materials follow this rule. Rubber bands, for example, are elastic. They return to their original shape, but their force extension graph is not a straight line, so they don't obey Hooke's law. In this lesson, we've explored how forces push, pull, stretch, squash, and even break things. We looked at all the key types of forces, from friction and weight to upthrust and magnetic force. You've also learned what it means for a force to be a vector quantity, what a resultant force is, and how Hooke's law helps us understand springs and materials. But we're just getting started. In the next chapter, we'll dive deeper into how forces affect movement, including acceleration, Newton's laws, and how to use the famous F equals m times a to solve real problems. So if you found this helpful, make sure to check out the other chapters in the playlist. Up next will be Chapter 3, Forces and Movement. I'll see you there.